Lesson 112. So in this lesson, we're going to wrap up vectors by taking a look at some particular application questions that can be solved with vector properties, okay? So the first thing we're going to look at is how vector can be applied in kinematics. In this question, in the diagram, you can see that there's a path in dotted, shown as a dotted line. Along the path, there are 2 points PO to indicate the initial position of an object, and P is any other position along this path. Okay, the blue vector V is there to indicate the velocity vector, and notice how it is parallel to the path itself. So any where along the path, it can be represented as a scalar multiple of this velocity vector. So how can we represent displacement in kinematics? Well, notice how displacement is really velocity times time. So if I use t to represent time, then in vector form, tv would be the displacement vector. Okay, and to get to the final position v of p, we can imagine that the displacement from PO to P is really to indicate that we have, the position vector of the object added by its displacement TV, so that we can come up with the new position of the object R. Okay, so position R of an object can then be shown as a vector equation R equals to R naught plus TV. So let's apply the idea to an actual problem. Here we have example 1. The position vector of boat A, t hours after it leaves harbor, is given by R1, t at times the vector 30, 15. Second boat B is passing near the harbor. Its position vector at time t is given by R2. So A, how far apart are the two boats at the time the first boat leaves the harbor? So we're really dealing with initial position when time is equal to 0. So at this time, I know that R1 is 0 times 30, 15. So that's 0, 0. And R2 would be 50 plus 0, so 50, and 5 plus 0 times 10, so 5. Okay, and we want the distance between the two boats, which means that it is the distance of the vector R1, R2. Okay, and so 50 squared minus 5 squared. If you take the difference between the two vectors, this is 2, 5, 2, 5, or approximately 50.2 kilometers, rounded to 3 significant figures. Okay. Question B. How fast is each boat traveling? Well, how fast means speed. And speed, like we know from before, is the magnitude of velocity. Having said that, we need to be able to identify the velocity vector from each equation of the boat. And velocity vector is what? This is a scalar multiple piece. So t 30, 15. So 30, 15 is v1. So its magnitude is 30 squared plus 15 squared, all square root, okay? Which works out to about 33.5 kilometers per hour. And if we do the same for the second boat, so magnitude of v2, so that boat has a v velocity vector of 10, 10. So we are talking about square root of 200, or about 14.1 kilometers per hour, if I round this to 3 significant figures. Okay. So moving on, part C. Are the boats in danger of colliding if one of the boats does not change course? So we're assuming that both boats will continue in the same straight path. So the question can be translated into a question of finding a point of intersection between the two boats or two lines at the same time. Like they have to be at the same point, right, at the same time. Okay, so one way of doing this is to first write our equations in parametric form. So T1 is 0 plus 30t, and y is 0 plus 15t, okay? And L2 is, what's the position? 50 plus 10t, and y is 5 plus 10t. Okay, so let's assume there is a POI. Okay, so we can set 30t equals to 50 plus 10t. What do we have? 20t is 50, t is 5 over 2. And setting y is the same. 15t is 5 plus 10t. 5t is 5, t equals to 1. So obviously, since these two t values, the values of t is not unique, right? Therefore, there is no point of intersection, or we can say that the boats will not collide. Okay, so they're safe. Example 2. A ranger spots a forest fire at 00 while on an observation tower located at -48 and 65. The ranger can move at a speed of 8 meters per second. So A, determine the velocity vector V, and then how long does it take for the ranger to arrive at the scene. Okay, so let's draw a diagram first. Maybe I'll use line here. Okay, so the fire is at 00 and the ranger is located at -48 and 65, like something like that. Let's not draw the scale, so that's fine. And then we are told that the ranger can move along this path, right? So V, let me make this a little bigger because I need it for later. Okay, so at a velocity of 8 meters per second. Okay, so that's the magnitude of this vector here. Okay, and then what I know also is the position of the ranger, which is -48, and this is 65, the entire height here. In order to find the velocity vector from its magnitude, I can translate this problem into saying I need to look for the x and y components of the velocity. Okay, so looking at the diagram here, we actually have a set of similar triangles, right? Comparing the positions of different things and a little triangle representing, the xy component of the velocity here. So in order to find the xy components, I can use similar triangles. Okay. I can compare the x component to 48. I can compare the y component to 65. And I can compare this actual speed to, the hypotenuse of the larger triangle, which is 48 squared plus 65 squared, all square root. Okay, so solving one pair of these ratios at a time, x is equal to 48 times 8, or 48 squared plus 65 squared. I think I get 6529. So this works out to 384 over 6529. Okay, so that's the x component. We are going towards the right, so it's positive. And then for the y component, we're going down. So we have to compensate, okay, when we write out the actual vector. But let's find the, relative length first. 65 times 8 over 6529. This works out to 520. Like that. Okay, so now we have these two x and y components. We can say that the velocity vector is, I can write it in common factor form, or for space, I can write it using I and j. And make sure this is minus 520 over 6529j, like that. Okay. So now having that velocity vector, how long does it take for the ranger to arrive at the scene? So at the scene, we're talking about where the fire is at 0, 0. And the general equation for these kinematics problems is that any position is equal to the initial position plus time times the velocity vector. So the actual position that we're looking at is 0i plus 0j, and this is equal to negative 48i plus 65j, that's the original position, plus t times 384, 6529 square root I minus 520, 6529, j, like that. And then we can compare the x components by x component and y by y. I have 0i equals to negative 48 plus 384, 6529 I, right? T here. This allows me to actually solve for t. I can rearrange like 48 equals to 384 t over square root of 6529. And so t works out to 10.1 seconds. Okay. So here is example 3. Line L has the equation r40 negative 1 plus lambda 11 negative 1. And point A is located at 2, 6, and negative 3. So two parts. A, find the coordinates of point B on L such that the line segment AB is perpendicular to L. So let me plot this imaginary perpendicular place. So B should be located there schematically, and then find the shortest distance from A to L. And of course, shortest distance is the perpendicular distance, which means that once we know the position or the coordinates of point B, then for part B, we are really looking for the magnitude of the vector AB or BA, doesn't matter, okay? What we know, since point B is located on the line, B must take on coordinates 4 plus lambda, 0 plus lambda, negative 1 minus lambda. Those are the coordinates of B, okay? And then knowing that because the line segment is perpendicular to L, that means the vector AB must have a dot product with the direction vector of the line that is equal to 0. Okay. So let's do this. I have 4 plus lambda minus A, which is 2, I have lambda minus 6, negative 1 minus lambda plus 3, dotted with the direction vector 1, 1, negative 1 equals to 0. Okay, so let's see. First line I have 4 minus 2, 2. So 2 plus lambda, when I multiply that by 1, plus lambda minus 6, I have 3 minus 1, 2. So negative 2 plus lambda equals to 0. Okay, so 1, 2, 3. 3 lambdas is equal to, so 2 minus 2 is gone, negative 6, so it becomes positive 6. So lambda is equal to 2. So substitute this value of lambda into, what we set the coordinates of BR. Therefore, point B should be located at 4 plus 2, 6, 2, negative 1 minus 2, negative 3. Okay. So now part B, the shortest distance. It is the magnitude of the vector AB. Okay. So we're looking for, what is this vector? 4 plus lambda minus 2. Like we can go back to, this line here, this part in the question and recycle it, right? Because lambda is now 2, so our 4 plus 2 minus 2 is 4. And then 2 minus 6 is negative 4. Negative 1 minus 2 is minus 3, so this is 0. So we're looking for the magnitude of the vector 4, negative 4, 0. This is 16, 16, 0, square root of 32, 16 times 2 of 4, root 2 units. Okay, we can find this exactly. Okay, so here are some examples of applications of vectors.